This slideshow will introduce the central limit theorem and give an application, which will hopefully help you to understand why the central limit theorem is so important and how it opens the door to inference, which will be the last and most important section of your AP Statistics course. This establishment is called Newton Fat Farm. A fat farm is a clinic, resort, or spa where people go to lose weight. The politically correct term today for a fat farm is a weight control retreat. People will go there to help lose weight or, in some cases, gain weight. Fat farms used to be quite Spartan, but today they are more like luxury resorts. This is Mr. Ted Tyree. Mr. Tyree is CEO of Newton Fat Farm, which, over the past few years, has become a very popular place for people to control their weight in a gorgeous setting. You are a reporter and have been chosen by your newspaper to write a story about Mr. Tyree's establishment, and particularly the clientele, the typical people who come to Newton for help with their weight. Mr. Tyree sits down with you, and you begin to conduct your interview. Your interview with Mr. Tyree begins, and you start by asking him how many people are presently residents at Newton Fat Farm. And he responds that we currently have 1,000 residents. Your second question is, what is the average weight of the residents at Newton Fat Farm? And his response is, for reasons of confidentiality, I don't choose to answer that question. So let's examine what we know and don't know. We know the population, the current residents at Newton Fat Farm. We know the population size, n equals 1,000. However, we don't know the population mean weight. Since this is a parameter, we use the Greek letter mu to describe the unknown population mean. Although Mr. Tyree will not tell you the average weight of his Newton population, he does invite you to tour the grounds and talk to the residents. He also gives you permission to ask any of them their current weight if they choose to divulge it. You realize that you could find out what you need to know, the average weight of people at Newton, by asking every one of them their weight, assuming they would tell you. That, we know, is called a census. Hopefully you realize, though, that it would be very difficult to find everyone and ask them this question. You realize that if you were ever going to know mu, you were going to have to estimate it by sampling. Walking out of Mr. Tyree's office, you encounter Pauline in the lobby, and you strike up a conversation with her. You ask her weight, and she has no problem telling you that she weighs 225 pounds. So our first question is, how confident are you that Pauline's weight of 225 pounds is, or is close to, the true mean mu of the 1,000 person population of Newton Fat Farm? A, very confident, B, fairly confident, C, not very confident, D, not confident at all. Hopefully you answered C, not very confident, or D, not confident at all. There are two reasons you might have done so. First, realize that choosing Pauline was a convenient sample. She was sitting there in the lobby and may have been the first person you saw. Second, realize that if you chose someone else and that person told you his or her weight, it would likely be very different from Pauline's weight. So statistically speaking, trying to estimate mu, our population mean, based on one observation, is quite ridiculous. It would be like trying to predict your final average in your English class based on one exam, or trying to predict the average cost of 100 items in a supermarket cart based on the price of one item. Rather than asking people the embarrassing question, how much do you weigh, Mr. Tyree gives you access to his files and allows you to choose 10 people at random, and he will tell you their weights. He uses his calculator to choose a simple random sample of 10 numbers from 1 to 1,000, and he then finds the corresponding person and his or her weight. Here are the results. Matt, 275 pounds. Rick, 412 pounds. Elena, 211 pounds. John, 325 pounds. Ken, 350 pounds. Lori, 109 pounds. Marty, 252 pounds. Elsabeth, 133 pounds. Avni, 101 pounds. John, 325 pounds. Notice that John was chosen twice. Realize that if you had asked people their weights, you wouldn't have asked the same person twice, but when choosing random numbers, it is quite possible that the same number can be chosen again and again. Also realize that although this is a fat farm, and many of the people are indeed quite large, there are people here who have weight issues and may actually want to gain weight. So what does this sample of 10 tell us? Below is a histogram of the weight distribution from our sample and our average of the sample, which is 250.3 pounds. Since this is a statistic, its proper notation is X bar. Obviously, with a sample size of only 10, the histogram doesn't tell us much. But do you think that the sample mean of 250.3 is representative of the unknown population mean? Statistically speaking, we are asking, how confident are you that the sample mean of X bar equals 250.3 is the same or is close to the unknown population mean mu? A, very confident. B, fairly confident. C, not very confident. D, I don't know. If you had trouble answering this question, don't worry. The best answer is probably D, I don't know. On the one hand, your sample of 10 had some large weights, but some small weights as well. Logic might indicate that these will balance out, and our sample mean of 250.3 may very well be close to the unknown population average. On the other hand, our sample size was quite small. If Rick at 412 pounds was an outlier, we know that our results could be skewed to the right, and the X bar of 250.3 might be too large. Mr. Tyree allows you to make repeated samples of 10 people. You do so 4 times, computing the mean of your sample X bar of 10 each time, as well as the sample standard deviation. Notice each time we get a different sample mean X bar along with different standard deviations. Hopefully, you can see why we should have been quite unsure whether our first X bar of 250.3 from the previous slides was our population mean mu. Since each of these samples is as likely as any other, if we tried to use that one sample to predict the population mean, then using any of these results would have led us to very different conclusions. Mr. Tyree allows you the use of his office for the afternoon, so you continue to take SRSs, random samples of 10 people. But now you just compute the average weight of these 10 people. You do so over and over again. You are creating a sampling distribution. The chart on the slide shows the first 15 of these averages. Notice that we had one average as high as 247 pounds and as low as 185 pounds, and any one of these could be our population mean mu. That is quite a gap. We make a histogram of these averages and find the mean of the average. Notice that the histogram is quite unlike the histogram we created before from one sample, that it has a feel of a normal curve. And also, the mean of 218.5 now very well may be a plausible estimation for mu, the average of our fat farm population. We continue to create our sampling distribution of size 10. We do this 250 times. We then create a dot plot of our sampling distribution as shown on the slide. Every one of these dots represents an average of 10 weights. Notice how the dot plot has a feeling of normality to it, a bell-shaped curve. We also compute the mean and standard deviation from it. If this data was truly normal, it would follow the 68, 95, 99.7% rule. That means that 95% of the data would lie within 2 standard deviations of the mean, or from about 180 to 255. This means that we would be about 95% sure that the true population mu would lie between 180 and 255. We are thus narrowing down what we believe the unknown mean mu is with a certain degree of confidence. Or put another way, since any of these dots could very well be the true population mean mu, it is much more likely that our mu is within 2 standard deviations of the mean 217.8 than one of the dots on the extremities. However, maybe the results we just viewed were an anomaly, dumb luck. Let's do our sampling distribution of choosing 250 samples of size 10 3 times. Notice how each result varies only slightly from the others. What we are saying is that the statistical results from these different sampling distributions are very predictable. The mean of the sampling distribution appears to be centered around 215 to 218. That means that the mean of the population should be in that interval as well. Notice that the standard deviations are somewhat the same, but do have some variation. Hopefully, you notice why the middle distribution has the largest standard deviation. That outlier of around 140 certainly contributes to it. And again, while any of these dots could possibly be the true population mean mu, it is much more likely that mu will come from the center of the distribution rather than the extremities because of the density of the dots in the center. Mr. Tyree adjusts his computer to give you random samples of the weights of 25 people rather than 10. Shown is a dot plot and the mean and standard deviation of the sample of 25. Note how the distribution has no resemblance to a normal distribution. In fact, it looks somewhat bimodal with two peaks. Still, the mean of the sample appears close to the interval in which we believe the population mean mu to be, between 215 and 218. So again, we look at three examples of sampling distributions of size 25. Notice how again the mean of all three examples appears to be in that 215 to 218 range. That seems to be even more evidence that the population mean is in that interval. However, there is a distinct difference between the sampling distribution of size n equals 10 shown previously and sampling distribution of size n equals 25. Do you see it? Notice how the means from a sampling distribution of size 10 and size 25 are practically the same, about 216.4. But notice how the standard deviation in sample size 25 is much lower. What does that mean? Remember that in real life we would not do this repeated sampling. We take one sample of size 10 or size 25, take the mean of those weights x bar, and believe or hope that it represents the population mean mu. Since the sampling distribution is normal, it follows the 68, 95, 99.7% rule. In the case of size 10, we would be 95% confident that our mean mu would lie between two standard deviations, that is 179 and 254. However, with sample size 25, using the 68, 95, 99.7% rule, we would be 95% confident that our population mean would be between about 193 and 240. So we are much more able to nail down the lower and upper bounds of what we believe the population mean mu is if we use a larger sample size. Let's do this one more time, this time with a sampling distribution of size 50. Notice how the mean doesn't change very much between 216 and 217. Also, realize how normal the sampling distribution appears, but notice how the standard deviation drops again. Again, remember that you are only going to take one sample of 50, not the 250 that you see here. However, since the standard deviation of the sampling distribution is so small, if your sample yields a mean of any one of the dots within two standard deviations of the mean, it wouldn't be very far from the true and unknown mean, mu. You might wonder if the standard deviation drops by increasing the sampling size, allowing you to better predict the lower and upper bounds of the unknown population mean mu, why not increase the sample size to 100 or 200 or more? Shown on the slide is a sampling distribution of size n equals 200. That is 250 samples of size 200. You are literally sampling 50,000 people, 50 times the population size. Notice how tightly packed the normal distribution is. That is borne out by the now small standard deviation of 4.5. Two standard deviations from the mean is now 207 to 227. Any one of the dots in those intervals is 95% likely to be your one sample of 200. If you used it to estimate the unknown population mean, you wouldn't be far off. So you can do a large sample size. But if you make the sample size too big, you can be dangerously close to actually doing a census, finding the weight of all 1,000 people. And if we do a census, we then can calculate the population mean mu, and all of this work is meaningless. So we want bigger sample sizes, but not too big. Later in the inference section, we will learn how big these sample sizes should be. So, in summary, we now present the central limit theorem. Read it. What the central limit theorem says is that if you take a large sample from any type of population and keep doing so, first, your distribution of sample means will be normal even if the population is not. Second, the mean of your sample x bar will be close to the unknown mean mu. And third, the standard deviation of the distribution of sample means will be close to the population standard deviation divided by the square root of n. So if your sample size n is large enough, the mean of your sample should be quite similar to the unknown population mean mu, the unknown for which you search. After realizing how much work you have done, Mr. Tyree relents and decides that he will give you the weights of all residents of Newton Fat Farm and thus answer your second question, the value of the population average mu. However, it doesn't matter, as you have pretty much determined it through sampling. But once you have all the weights, you can examine the distribution of the population. Notice that the population is bimodal with two peaks, almost like two normal distributions. That makes sense, as the people most likely to go to Newton Fat Farm are people who want to lose weight because they are so heavy, and people who want to gain weight. As one would think at a place like Newton Fat Farm, the majority of people are fat. The distribution is certainly not normal, far from it, but that doesn't violate the central limit theorem, which says that the sampling distribution will only appear normal if the sample size n is large. Notice also that the population standard deviation sigma is 60.47. If you take sampling distributions of size 10, the standard deviation should be 60.47 divided by the square root of 10, which is approximately 19, and that fits what we saw on previous slides. If we take sampling distributions of size 50, the standard deviation should be 60.47 divided by the square root of 50, which is approximately 8.6, and that fits what we saw on a previous slide. When we want to estimate the mean of a population mu, the central limit theorem allows us to take a sample of large size, 30 is usually a good start, and calculate the sample mean x bar. We can be reasonably sure that the sample mean is a good estimate of the population mean mu. The larger the sample size n, the more confidence we have in our answer. We can use the central limit theorem on populations that are normal or decidedly not normal.